A cell-based architecture has been made pretty much a golden standard for large applications nowadays, and it's been made popular by big cloud providers such as AWS of Amazon and Microsoft. And the reason is, nowadays, these big applications that serve millions of users every day, they're relying on cloud technologies, and they need to be very, very resilient. Now, we're going to talk about which kind of applications are best suited for the cell-based architecture, but we're going to start with a fun fact first. I actually mentioned this pattern in the previous video on multi-tenancy, and I mentioned a pattern called a bulkhead pattern. Bulkhead pattern is exactly the same thing as a cell-based architecture, okay? What is a bulkhead in other words? Well, everyone knows this bottom part of the ship, pretty much seen the Titanic movie, where if one part of this bulkhead, the whole thing is a bulkhead, right, is damaged and there's water, we have to make sure that it doesn't spill over other sections of the boat, okay, so that we can prevent the spillage. You can apply the same thing to application architecture, okay, the same thing here. And with that said, we're gonna learn what a cell-based architecture is, why you want to use it or why you need to use it and in which cases, and of course, how to design it, because designing it is probably the most interesting part, because you have to take into account not only your application layer, but also the storage and load balancing. So it's gonna get pretty interesting. And of course, we're gonna talk about best practices as always. If you're ready, make sure to subscribe or already like the video, because I'm pretty sure you're gonna like the whole video without even watching it. And let's get started. Alrighty, so we're gonna try to compare these two paradigms, all right? So the usual way of building applications is this one. So I would say small to medium-sized application. We will usually have a load balancer, and we're also going to have our application layer, meaning our API, for example, and we can auto-scale, okay? We can create these nodes on demand, and then the application load balancer will be able to route the incoming request accordingly based on how busy a specific container or a process is. And we also have our storage. Let's say it's a database, but we can also either shard it, okay, or we can create read replicas, meaning this is going to be a read-write replica. This is going to be a read replica just to offload some of the processing powers, okay? But for larger applications, we're going to be using cells, and I want you to focus on this part. Okay, cell 1, cell 2, and cell 3. And as you notice, all of them have a load balancer, okay? All of them have the application layer nodes, let's say ECS or EC2 container instances or just containers, and all of them have their own storage. Now they are completely isolated from each other, okay? They're not able to talk to each other, and this is the best part, okay? The cell router now is acting as a load balancer, although we're not calling it a load balancer because it's a much simpler thing. It's not able to do the things that a normal load balancer will be able to do. It's only route on requests, and that is it, okay? It's gonna route the requests based on what the control plane is gonna tell it. Okay, we're gonna talk about this in a couple of minutes, but basically the cell router is only routing the request, and this is it. Now, let's talk about this interesting separation between these cells. So they are basically organisms that can live on their own without needing to contact another cell, okay? Now, why would you do this? Okay, first of all, or how would you do this? Well, you could, first of all, split them by geography, okay, with a geographical region. Meaning cell 1 is going to be in the US and cell 2 is going to be in Europe. Cell 3 can be in Africa or in other part of the world, in somewhere in Asia, in South America, or Australia, of course. And the reason is, let's say if we are an e-commerce shop and something happens to our cell in the US, our US customers are not able to access it, but our customers from Asia are still going to be able to access it. Okay, let's say geographical region. Something we talked about in the previous video, tenant. We can also separate it based on a customer or a tenant or organization. User segments, let's say we can say normal users are going to be routed to cell 1, but users with a priority, meaning they paid extra to be able to have a higher availability, are going to be routed to another cell. If you use domain-driven development, and I actually have a video on DDD, we can also separate them by features. Why not? Also compliance, maybe, for example, Europe has stricter regulations, so it doesn't let you store data in a way that the US does, right? For example, and of course, workload type. Maybe one of the cells needs real-time messaging and another one actually works with historical data. So you can actually divide them based on the workload type. Now, let's talk about why would you even use a cell-based architecture, okay? Maybe it's not still clear from these points. I bet it's not, because it usually wouldn't be. But here are some points that I sketched out. So for example, horizontal scaling, okay? So it's much easier to simply create a new cell here and make sure that you create a separate organism, let's say, that can live by itself and it's not going to be affected by another cell. Also, lower scope of impact. Let's say in a typical workload, if one of your, let's say, service is damaged or is not working properly, 100% of the customers are unavailable, right? None of your customers is going to be able to reach your application. In a cell-based workload, only 1/3 of the customers are going to be unavailable, as we talked before. Also, it's still good for vertical scaling, meaning sure, you can create new cells on demand, but you can also scale it vertically. Like one cell can have more CPU power and more RAM compared to other cells based on your needs. Also, it's much easier to test. Actually, you can simply test one cell and then you're going to know that other cells, as long as the code is the same, they're going to work as well. Also, higher mean time in between failure, lower mean time to recovery, meaning you can actually fix the problems in one of the cells much faster compared to when your whole system is down, all right? That's also self-explanatory. And also, it's much easier to do deployments and rollbacks. Rolling back only one cell, it's a much simpler thing than rolling back all the data in all the cells, okay? And of course, using or making use of things like worker pools, rate limiting, and circuit breaking is also a necessary part of resilience, because this topic is basically resilience, how to make our large application more resilient to failures. And you can use these 3 points. Actually, I have videos on rate limiting and circuit breakers, so check them out and make sure to subscribe to learn more about this kind of topics and have these nice dashboard sessions. Also, let me know if you like them. And yeah, as I said, make sure to subscribe. All right, I'm gonna leave the links to both of these topics in the video description, so don't miss it out. Also, when we talked about vertical scaling, as you can see, maybe adding more power to cell 2 is actually more meaningful, okay? So this is about the reasons why one would use a cell-based architecture. Now, when do you need to decide whether it's worth going for cell-based architecture or not? Well, you usually would need to ask yourself this question. Is it better for 100% of customers to experience a 5% failure rate, or 5% of customers to experience a 100% failure? This pretty much depends on these points. So if it's an ultra-scale system, large-scale application, that is kind of critical. Let's say it's a finance app, or maybe it's a government application, but not necessarily. Again, it can be just an e-commerce shop. Or if it's a multi-tenant service, where some tenants simply require fully dedicated tenants. For example, you're a factory and you're using an application for your factory and you don't want any standstills, you can use cell-based application to make sure that your factory at least always is able to process some amount of data, okay? Now, let's quickly talk about the scenarios when cell-based architecture actually wouldn't make sense. Let's be honest, it's a cool feature, but it doesn't always make sense. For example, for startups and MVPs. I mean, this will be basically over-engineering. You can simply go for a monolithic architecture or simple microservices. Also, trading applications or like real-time trading. Actually, trading would be critical, like finance, like banking, that would be critical. And this would be a good candidate for cell-based architecture. But real-time trading would actually not be a good way, because you would need, it would be hard to manage consistency across multiple cells. Instead, you can just simply do sharding, okay? Also, real-time scenarios like multiplayer games, machine learning and training and big data. Basically, it's much easier to work with centralized data and highly regulated data because of some compliance issues. All right, also, what it means is that the complexity is now growing, okay? There's some redundant infrastructure because you're literally copying the same schema multiple times, all right? We have the same thing copied 3 times. Somebody has to manage this. Also, it's costlier. It's much easier to simply auto-scale here and create new instances, EC2 instances or ECS instances, rather than creating new cells, because these are actually new machines in different availability zones, in different parts of the world. Also, you will probably need specialized operational tools or actually people to be able to operate these different cells, okay? Now, let's jump to the next topic. Let's dive a bit deeper into the architecture of this paradigm, all right? So, at least in AWS, this is how the naming goes. We have a control plane, and as you can expect, control plane is basically the brain of the cell-based architecture. And we also have a data plane. Data plane is including the router and our cells. So the control plane is going to be able to dictate the data plane some things. For example, how to route the traffic, the service discovery, like which services are available. It can also do the role of an API gateway and authentication. It can do the cell orchestration, meaning which cells are down, which are not. And it can do the observability, it can do the logging and the deployment management. And these are the corresponding AWS services that can do it for you. For example, Lambda, Amazon API Gateway, Cognito, of course, Amazon Lambda if you want your personal orchestration or private orchestration application, Amazon CloudWatch for logs and code deploy. Now, the thing is, Amazon doesn't offer any managed service right off the box for cell-based architecture. You have to assemble these parts yourself, which kind of makes sense, right? And you can not only do it on AWS, but on Azure or Google Cloud as well. So actually anywhere. Now the data plane, this part, the right part, is simply a bunch of compute layers like Amazon EC2 instances, storages obviously, message processing like SQS, RabbitMQ, and caching if you want to. Now, a simple example would be that each cell runs its own AWS virtual private cloud in different availability zones, obviously. Also, yeah, as I said, they're distributed across multiple AWS regions. Also, Route 53 or an API gateway is going to route the users to the closest cell. Then DynamoDB or EC2 instance is within the data plane, and you can do auto scaling within those cells if you need to. All right, again, the same picture and pretty much the last thing that I want to mention, which is the cell design. Okay, usually these cells are going to be totally isolated from each other. Some say, at least the Amazon recommends to create even separate accounts for these cells, literally separate user accounts for these cells so that they have no point of contact. That's how isolated Amazon recommends them to be. Okay, but there are some scenarios where it actually makes sense to let a cell to span across multiple availability zones. So imagine cell 3 is not only within Europe or US, but it's also at the same time both in Europe, in the US, and even in Africa. Okay, so 3 different continents. Why? Well, let's say we want even extra resilience. We want that if our European customers are facing issues and the zone is basically down, European customers still can access the data that's stored in Africa. Okay. Now, this kind of adds more latency, but it's also more expensive, but now we have higher resilience. Also, we have this interesting architecture where every service within an availability zone is going to be its own cell, okay? You can also have this granularity. Now, this is of course cheaper, but each cell communicating with each other for the sake of resilience is going to probably impact the response times between the communication while they're communicating with each other, okay? So I'm gonna leave a link if you want to read about these design principles, but all in all, usually what you would see is one cell within one availability zone, okay? I hope you guys liked this video and learned something new. If you did, as always, at the end of the video, I'm gonna ask you to subscribe and share it with your friends, or simply destroy this like button. And I'm gonna see you guys in the next one. Goodbye.